So today I want to talk about force, but before we get there, I kind of want to review the tools that we have already in our kind of bag of tricks to solve or predict problems. We have graphical analysis, which is probably the most comprehensive, meaning that no matter what the object is doing, it's going to work. We could graph it, position versus time, and then interpret it into velocity versus time, and then interpret it into acceleration versus time. It doesn't have to be constant acceleration. It could be changing acceleration and it'll still work. It just takes a lot of time to graph and find slopes. Now for equation of motion, we kind of cut that in half because we use equations or variables to represent those graphs, and then we came up with equations that could solve the problems. Now the limitations on that is you have to have constant acceleration, like gravity. Now forces are kind of similar to that. You still have limitations. You still need to have constant acceleration for it to work, but it is another way to solve the same problem. So you can see here there's different pictures of different types of forces that we might encounter, but today we really want to highlight the bottom right picture, which is Newton. I know it's kind of a weird picture, but Newton was not in a suit. And the apple story is that an apple fell on his head and he kind of started thinking about motion in general. In class, we kind of did a slinky drop, and what I liked about it is that it forces you to think and try to predict what's happening. Right now, you don't have the tools of forces or even waves, so it's going to be a little bit difficult, but hopefully by the end of the period or end of this kind of little clip, you could try to describe what's happening with forces, and that's kind of the goal. But what I really like about it is that's how all sciences are. You look at a motion and you try to figure out why and try to predict what's going to happen in the future. Based on the experiments that you've done. Okay, back to definitions though. So what is a force? Here you have the force lifting rocks, which is the opposite of gravity. So that kind of is what force is, not metachlorines, but gravity. So it's a push or pull. Gravity pulls you down. And we have both contact and non-contact forces. So contact is pretty straightforward. If I just hit you, that's applied force. So I could write that as well. So that's applied. So if I hit you, it's force applied. And it's kind of a general term for like punching, pushing, kicking, ball hitting something. So when you don't know how to label it, or you just don't want to be too specific, you could just say force applied. So a person pushed it, force applied. You have stuff like friction, normal force, which we'll talk about, which is surface, spring and tension, and all these things are forces that need to touch the object in order for it to have motion. We have other kind of forces which are non-contact, so gravity, magnetism, strong and weak forces, and electrostatic, which I'll add right here, are forces that you actually don't need. They could go through a medium or the lack of and still work. And that's what's kind of important because gravity goes through no medium. So no air, you don't need air for it to work. It's going to pull, and that's what keeps us on Earth, but it also keeps the Earth in orbit around the sun. Today, before we get to Newton, I do want to remind us what scalars and vectors are. Scalars, remember, is just a magnitude, while vectors is also a direction. So in the case here, force is actually a vector. It has both a direction and a magnitude. I push you up, I push you down. Gravity is always pulling me down. Gravity can't change, but that's what it's doing. It's pulling me towards the center there. So that is a direction. Things I left out just for the sake of review. Scalar, you have time. You can't go backwards in time, at least not yet. And then here, just remember force is also a vector. All right, Newton's laws. He came up with the following, and it was really impressive because during his time, people thought the natural state of an object was rest, right? And it kind of makes sense. Right now I'm at rest. It takes energy for me to move, and then once I move, I end up at rest. If I throw a ball, it's also going to eventually end up at rest. So that's what people thought the natural state was, rest. Now, for Newton, he thought completely out of the box. He said, no, the natural state of an object is actually in motion. So he thought things are going to stay in motion until a force acts upon it. And that's his first law. So whether it's at rest or in motion, it's not going to change its motion unless a force acts on it. So it's also kind of called inertia. Inertia is just I guess the best way is the resistance and change of motion. So if you're at 0, your inertia wants to stay at 0. If you're moving at 10 meters per second, that's your inertia, and it wants to stay at that as long as possible until a force acts on it. Now, certain objects might have more inertia, some might not have enough, but anyway, inertia is just a resistance to change. Newton's second law is probably the most famous, and that is the one that you probably learned in 8th grade or 8th middle school science, which is force is equal to ma. Now, when you read it, you'll notice that he kind of doesn't talk about mass and acceleration, which is what we learned. Force causes a mass to accelerate. He actually talks about momentum per change in time. It's kind of weird, but if you rearrange this, remember that acceleration is change in velocity over time, right? Change in velocity is vf minus vi. That over time gives you acceleration. But he kind of saw this kind of relationship like this, where you have mass times change in velocity over time. This is technically, or it is called momentum. So that's kind of how Newton thought of force. And it makes sense because momentum is probably the best way to explain inertia, right? If something has more momentum, it has more inertia, or least likely to change, right? So think about like a really big object. Once it's in motion, it takes a lot of force to stop it in motion, which is what inertia is. So he thought is you have an object in motion, and a force over time is what causes it to change. Either way are fine. I kind of like this one. Force causes a mass to accelerate, but they're both the same thing. Now the last one we'll kind of come across probably in a few weeks or a week or so, and that is for every action there's an equal and opposite reaction. So if I punch a ball, I'm going to feel the fact that I punched a ball. There is some force that's going to hit me back, and it's going to be the same. So if I punch a ball at 10 newtons, it's going to punch me back at 10 newtons. So that's kind of that. Now there are some conceptual, I guess, challenges from this, and then we'll get there in a week or so and talk about the misconceptions typically from the third law. All right, kind of examples. One way to kind of break down Newton's law is always to, or at least see all the forces acting on you, is to do something called free body diagrams, or FBD. So free body diagrams are just a way to kind of draw all the different forces acting on a person. So right now, here I am standing up, so I am not moving. So the best way of saying that is my acceleration is 0. Okay, but I actually do have forces pulling on me. I feel gravity pulling me down. So I do have force of gravity, and it's negative. But I'm not falling to the center where something's pushing me up, and that's the ground. Now, in this case, these two are equal and opposite. Now, oh, sorry, I forgot to do one thing. Force of ground, another way of explaining it is force normal. So either way is fine, but the more common one is force normal. And just to kind of define it, normal force, or force normal, is the force supplied by and surface, and it's always perpendicular. All right, so what does that mean? Well, that means here's the ground, and this, if I kind of go like that, forms a right angle. How's that significant as well? Well, let's say you're parking on a hill. So here's my amazing car. and it's parking on a hill, gravity, no matter what, is always pulling down. In this case, this is not Fn. Right, it's not opposite of gravity. Fn is actually perpendicular to the surface. The surface has an angle, so I'm going to draw an Fn perpendicular to the surface. Okay, so we'll eventually get to problems at angles, but for now, we're just going to deal with this. But just know, normal force is force applied by a surface, and the force is perpendicular to that surface. All right, in this case, we want to analyze what's going on. So what we normally do is something called sum of all forces. Let me kind of get rid of something. Okay. The sum of all forces can be written two ways. You could do F net or the actual sign, summation of forces. I use both, and the reason why is some books will use F net, some books will use sum of all forces. I interchange it, bad habit, but I've learned from different books. I probably will stick with this one because we're eventually going to talk about either in the y direction or the x direction. In this case, it's the y direction. So here we have sum of all forces in the y direction is force normal plus force of gravity. Now, since I'm not moving, I know these are equal and opposite. So if they're equal and opposite, the sum of these two is 0. This tells me what's going on, even though I have multiple forces acting on me. Gravity wants me to go down, but the ground is pushing me back up. So those two are working against each other. So in the end, I'm not accelerating. Okay, so that's kind of the cool thing about sum of forces. It tells us what's going on. Is it going to be a positive, a negative, or even a 0? In this case, it's a 0. All right. Skydiving is a great example of different types of forces as you're falling down. So I like this one because it's quick. It's like a 30-minute jump, not 30-minute, a 30-second jump. And you can see them kind of go through different stages of their flight. So I just kind of Googled random pictures. Here we have a person jumping out initially. Here it hits something called terminal velocity, which I'll kind of explain. Pretty much what terminal velocity means, it eventually can't go any faster. And it'll make sense in a bit, but let's just say its terminal velocity is equal to, I'm going to make up a number, 100 meters per second. All right, and then you have the parachute open. Now, if you watch the video, the jumper initially will kind of go slow. And the reason is because when he jumps out of the plane, technically VI is equal to 0, right? Unless the plane is going up or down. If the plane is going horizontal, when the person kind of just leaps out of the plane, their VI is 0. Now, at the very beginning, you're going 0, but you're going to speed up negatively. Why? Well, there's two forces acting on this person. Actually, probably just one initially. You have force of gravity, and then you have a very, very tiny force of air friction on the very top. Now, eventually, as it keeps falling, gravity never changes. Gravity is always pulling you the same amount. So hopefully I showed that with my arrows. But as you're going faster and faster, air resistance is going to get bigger and bigger. Look how small it was initially, and now it's much, much bigger. Well, it kind of makes sense. Well, think about this. If you're driving your car, and at 5 miles per hour you stick your hand out, you might feel like tiny bit of wind, but your hand is not going to move. Do the same thing at 30. Your hand probably won't move, but you're going to really feel wind against your hand. Now, if you did the same thing at, like, let's say 100 miles per hour, I don't recommend, your hand might actually be blown back because now you're going and cutting through that much air. Well, the air around your car is moving as well, 100 miles per hour. So as you go faster, this force of air friction gets bigger. Now, eventually, they're going to be the same size. And once they're the same size, you hit something called terminal velocity. Now, the last one, I'm going to try to draw my gravity the same. And when the parachute opens, it initially has a very big force of air friction. Now, remember, when you're falling, you have a small, I guess, cross section, but when you open up the parachute, it has a big one, so it catches a lot of air or air friction, and it slows down. Well, how is this significant? Well, let me show you. If we think of sum of all forces, in the first one you have sum of all forces in the y direction is force of gravity plus force of air friction. Now, when you look at it, that's the same for all of them. So just know that that's the same setup equation. But right now we want to kind of see the relationship between these two. So here we have force of gravity, force of air resistance, and here gravity is bigger. Well, if gravity is bigger, it's going to go down. I'm going to try to show that in this equation. So remember, gravity is negative, air friction in this case is positive. If Fg is bigger, then my sum of all forces is negative. That means you're going to accelerate down, which the person does. At terminal velocity, we have the same setup. Force of y, Fg plus F of AR, and equals positive or negative. Here, Fg is equal to AR. Remember, they're equal and opposite, so that means these two plus together, equal and opposite, will kind of still give us 0, right? Negative Fg plus that one will give us 0. So that's why we have a constant velocity, is because we have 0 acceleration. Now in this case, sum of all forces in y, Fg plus F of AR. In this case, AR is bigger, or air resistance. So now if this is negative, this is positive, you're going to get a positive number. So here, gravity's bigger, so you're going to fall down. Here, they're equal, so you're not going to speed up or slow down. You're going to stay constant or terminal velocity. Here, the parachute opens and it sucks you back up. Eventually, the parachute will also hit, what's it called? Terminal velocity, but it should be much slower, or else what's the purpose of a parachute? Also, how you're kind of flying around in the air will kind of determine how aerodynamic or not aerodynamic you'll be. So if you're more aerodynamic, you should be able to get a higher terminal velocity versus somebody who's spread out. Now, let's look at other examples. Here we have a Tesla car, and you're going to have force of gravity, force normal. Now we really don't care about this one because the car isn't moving up or down, but for the sake of just writing it, sum of force in the y is Fg plus Fn. Since it's not falling or climbing or being pushed up, 0, right? Equal and opposites. Now this is not going to be 0. And you could think about it. Or, not going to be just those two. You could think about it. If you are driving your car and you want to maintain 30 miles per hour, you don't let go of the gas pedal. Once you get there, you have to keep it on to kind of help it move forward. So you have force of the car, which is trying to fight force of air resistance and friction against the road, which we'll just call friction. So this A has to overcome these two. So if it's constant, sum of all force in the x direction, you have force of AR, and then you have force of friction, which is the rolling resistance, and then you have FA. Now all these added together has to give you 0 because we have constant speed. Now if we didn't have constant speed, which is the next slide, then now this must be bigger. So if the car is accelerating, technically you don't know which way, but if the car is accelerating, then you know sum of all forces is not 0. So in this case, it's going forward. Sum of all forces is equal to positive because this one must be bigger, this one must be bigger than these two. So that means we're going to accelerate forward. Now the bottle trick is actually pretty cool. So if you actually get a bottle and try to rip out a dollar bill, empty glass bottle, it won't really work. It's going to keep tipping over every single time. Now there is reason for that because it's top heavy. So most of the weight is up here. If I might get my pen to work, most of the weight is up here. So when you pull it, what's going to happen is here you have a balance force of Fg and Fn. And then when you yank on it, you just have friction. And that's it. You don't have force applied because the paper is moving to one side. Now, if you move fast enough, sometimes you get the force of friction pretty small, or it's so fast that the object doesn't react to it because of its inertia. But in this case, it's going to be hard. You're going to pull, you're going to have unbalanced force going this way, so the bottle's going to tip this way. How can we solve it? Well, the parlor trick is instead of yanking out the dollar is, so this is the, whoop. So let's say this is the dollar, my drawing. Instead of pulling it, let's say to the left, force applied, I'm going to do something else. I'm going to roll it up. And roll it up until it pushes off the bottle. And the reason why this works compared to the other one is now you have not only you're pushing it this way, force applied, and you get force of friction this way. Now, force applied is technically bigger than force of friction, but not very much. So in that case, since you do have semi-balanced forces, it's not going to tip over. Mythbusters does a really good episode of the tablecloth trick, and you can watch that if you want. And then kind of go back to this. I like you to try to think about it. How would you explain that slinky in terms of force?